There are a number of different factors that influence the rate of reaction. So one is temperature, and that's the one we're going to measure today. We're using Alka-Seltzer tablets. They're just basically effervescent tablets. They have an acid and a carbonate in them, and when you dissolve them in water, they undergo a reaction that produces carbon dioxide. And the rate of that reaction is what we're actually influencing. We're going to influence it using temperature, which is one of the things that influences rate of reaction. Another is surface area. The tablets are quite large. If we were to break it in half, we'd slightly increase the surface area. If we were to smash it into many small pieces, we'd increase the surface area a lot, and therefore the rate of reaction. If we were to put it in a mortar and pestle and grind it to powder, we'd increase the surface area even more and speed up the reaction. So that's another one. Another one is a catalyst. There's not a catalyst for this particular reaction, but for some reactions there's a catalyst that you can use that doesn't participate in the reaction, but allows it to happen more quickly. So there's a number of those. So we're using tap water, cold tap water. Our temperature probe tells us 22, just let it equilibrate a little bit, 23 point. That seems to be set along on 23.7 degrees. I'll take the tablet, drop it in, and we're just going to time how long it takes for the tablet from when I drop it in until it's completely dissolved. So I'll hit the start button at the same time. You can see it's fizzing pretty wildly at the bottom at this temperature. It floats up at some point because the gases around the tablet are strong enough to sufficient to make it float, and it'll float to the top. It'll keep dissolving, struggling to see it a little bit, but I think it's completely gone. Not quite. Now, I think it's done. So that's about 36 seconds, 35.98 seconds at that temperature. Now we'd expect, as we know with the rate of reaction, that if we use colder water, it will happen more slowly. If we use hotter water, it will happen more quickly. So let's do the cold one first, because it will be probably easier because it'll take longer to happen. So I'm going to fill this from just decanting it off the ice. So we'll see that temperature should be quite a bit lower than the 23.7 that we had for that trial. Try and fill the beaker to about the same level, although the specific measurement is not so crucial. And we'll check. Have to give the probe a moment to come to that temperature because it's a lot colder than the probe itself is. And that seems to have stabilized at about 6.3 degrees Celsius. So it's not zero, it's close to freezing point, but not quite zero. So around about 6.3, and we'll do the same thing. Time how long it takes to react completely. You can see the fizzing rate is there, but it's slower. It'll take longer before the step where it floats up. So we're at 30 seconds, we're at about the 35 that it took to react completely in the other temperature. And it still hasn't really risen from the bottom, and it's still quite a solid looking tablet. So it's going to take quite a bit longer to happen. It's just at a minute. and that's about 70 seconds. So that's about twice as long as it took last time. It hasn't actually floated. It's made some gestures, but it's just starting to disintegrate at the bottom instead. And a little bit floats to the top, but there's not much left. And that's it at 1 minute 44.62. So 144 seconds, 0.62 at the temperature of 6.3 degrees. So the final one we'll try is the hottest water that we can get. I believe hot tap water in Australia is regulated to about 60 degrees as a maximum. So we'll find out whether our lab is compliant, and we'll reset the clock in the meantime. So it's stabilised at about 50 degrees. 50.0 degrees, and it seems to be quite stable at that. So what we predict is that this will be a lot quicker. It won't take 36 seconds. So I'm going to have to be quick on the stopwatch, and we'll see how long it takes at this significantly higher temperature. You can see it's gone to the top immediately. It's fizzing much more strongly. You can see vapors coming off the top of the beaker. It's very difficult to see whether it's gone because it's covered in bubbles, but I can see it there. Disappearing very quickly, and it's gone in 21.18 seconds. So you can see that that's significantly quicker. And that's the effect of temperature. And as I say, we could actually do more temperatures. We could get nearly boiling water. We could get cold water with ice, with salt to lower the temperature as well. We could also be changing the surface area or using a catalyst to change the rates of reaction.